we done with triangles. We're going to start talking about other kinds of polygons. The first thing we have to do, though, to talk about that is to talk about what is a polygon. So a polygon, we'll get to these vocabulary words in a minute, but a polygon is a shape that's made of 3 or more segments that all intersect at their end points. Okay? So, for instance, a triangle, like just picture a triangle. Those are 3 segments, straight lines, right, that all intersect at their end points. Okay? So that's 3 sides. That would be a polygon. Okay? Now, vocabulary-wise, a polygon has sides and vertices. Sides, obviously, sides. Vertices are just like in a triangle. They're the corners. Those are the vertices. Okay? Now, one word that we might not know yet is a diagonal. A diagonal is a segment that connects non-consecutive vertices. Non-consecutive means not in a row. So if I look at this angle, this is a consecutive angle, so I can't use it to draw a diagonal. This is a non-consecutive angle because it skips one. It's not right in a row. All right? All right. Different polygons have different names. A quadrilateral means it has 4 sides, so that would be an example. Okay, take a minute and fill out this chart and see how many you know. Okay, so I filled out this chart. Hopefully you did too. A pentagon has 5 sides. Hexagon has 6. A heptagon has 7. An octagon has 8. Nonagon has 9. Decagon has 10. These prefixes should hopefully sound familiar. Now, we don't use it much, but a unigon has 11 sides. You don't see that used very much, though. And a dodecagon has 12 sides. Now, once you get past that, you start calling them n-gons, like a 13-gon or a 20-gon. You just start using the name or the number in the name. And so n-gon would have n sides. Okay? So let's take a second and see if we can figure out which of these are polygons, and then once we know they're a polygon, let's name them. All right, so I look at this shape. It's connecting at its endpoints, all straight lines. So it's a polygon, and there's 1, 2, 3, 4, 5 sides. So this must be a pentagon. Okay? This one does not all meet at the endpoints because these 2 lines there are intersecting in their middle. So this is not a pentagon, or not a polygon, sorry. This one is also not a polygon because it doesn't all connect at their endpoints. There's this big hole there at the top. All right? This one connects at their endpoints, or kind of should. It's kind of hard to draw on here. All right, so this is a polygon, and it's called a 1, 2, 3, 4, 5, 6. This is a hexagon. Okay, take a second and see if you can name these 4 and decide if they're polygons or not. All right, this one is not because it intersects not at an endpoint, right in the middle. This one it intersects at all endpoints, so it is a polygon, and it's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decagon, because it has 10 sides. Okay? This one intersects all at endpoints, so it's a 1, 2, 3, 4, 5, 6, 7. It's a heptagon. Okay? This one, last one, is not made of all segments. This one is curved, so it's not a line segment. So this is not a polygon. Okay? Now, one more. Polygons can be broken up into 2 sets, 2 different ways. One is they can be regular or irregular. A regular polygon has all equal sides and equal angles. So this is a quadrilateral, but so could this be a quadrilateral? This is a quadrilateral. There's lots of different quadrilaterals, but there's only one quadrilateral that has all equal sides and equal angles. So just so happens it's called a square. So the square is the one example of a regular quadrilateral. What's example of a regular triangle? Which triangle has all equal sides and equal angles? Okay, it's an equilateral. So the equilateral triangle is the regular polygon. Okay, now the irregular polygons is everything else. So here's the examples of 3 different irregular quadrilaterals. Okay, every other triangle, a right triangle, a isosceles triangle, those are all irregular polygons. Okay, you're probably used to seeing, like if you think of a shape, like if I ask you to draw a pentagon, you might draw that. Okay, that we always think of those regular shapes, but when you look back at the list we made, like for a couple of them I drew a regular pentagon, a regular hexagon, but this is not a regular nonagon. This is not a regular decagon, right? Because they're not all equal sides and equal angles. Okay. The other way to think about a polygon is either concave or convex. And it means just like it does in science, concave means everything, all the angles are pointing out. Okay? And the other characteristics of a convex polygon is that when I draw diagonals that, remember, intersect or join non-consecutive angles, they all occur inside the shape. So like if I were going to draw diagonals of a hexagon, okay, and I draw to non-consecutive angles, they're all going to be inside the shape, right? Okay. Concave means they are if you draw a diagonal between some non-consecutive angles, like see here's an angle, there's one, and there's one, so these two are non-consecutive, the diagonal could be outside the shape. Okay? And an easy way to tell is it's got a dent. Somebody kicked in a corner. So a concave polygon will have one angle at least that points in. So lots of those ones I drew back before were concave. Okay? So let's take a second and see if we can identify these as regular or irregular, concave or convex. Okay, this has all equal sides and equal angles, so it's regular. And all the angles point out, right? So it's convex. Okay. This one has all equal sides, but it doesn't have all equal angles because obviously this angle is smaller than that angle. So this is irregular, and some angles are pointing out, but some angles are pointing in. So that makes it concave. Okay? This one has all equal angles, but only sets of sides are equal. So these two sides are equal, these two sides are equal, but they're not all equal. So that makes it irregular. But all the angles are pointing out, so it's convex. All right. This one is irregular, and some of the angles are going in, so it's irregular concave. Okay. Now, to show you to talk about the inside of the polygon angle theorem, the way you can really think about the angles inside a triangle, like we all know that if I add up the angles inside this triangle, I get 180. Okay? Well, I'm going to use that to come up with how many degrees are always inside a quadrilateral, and how many degrees are always inside a pentagon, and how many degrees are always inside a hexagon, because they're all constant. So let's fill out this little chart. So in a triangle, there's 3 sides. I can draw diagonals in. Well, in a triangle, I can't because all the sides are consecutive. So I just get one triangle out of it. And the total number of degrees is 180. Okay? Now, if I draw diagonals of non-consecutive sides that make triangles, and I don't want to I don't want to create any angles inside the shape, only create angles that use the outside angles of the shape. So this makes, if I draw in this diagonal, okay, I make 2 triangles, right? Each one of these triangles is using angles that belong to the outside angles of this quadrilateral. And each triangle is 180 degrees. So this set of angles is 180 degrees. This set of angles is 180 degrees. So in a 4-sided figure, I can make 2 triangles, and the total number of degrees would be 2 times 180, or 360. Okay? Let's do a pentagon. A pentagon, to draw diagonals non-consecutive corners, I go over here, and I can go down there, right? And those all use angles that are on the outside of the shape. There are 3 triangles. Each one of them is 180. So in a 5-sided figure, I can make 3 triangles, and the total number of degrees, when I add up all the shapes, is 3 times 180, or 540. Okay, why don't you take a minute and try to do the hexagon and the hexagon and octagon. Okay, so if I look for some patterns here, I see that when a polygon has 4 sides, I can make 2 triangles, and the number of degrees is the number of triangles I can make times 180. 5 sides makes 3 triangles, and that's the total number of degrees is 3 times 180. 6 sides makes 4 triangles. 4 times 180 is 720. 8 sides makes 6 triangles. 6 times 180 is 1040. So if I think about what I'm doing here, every single time I took the number of sides, let's call it n, number of sides, I subtracted 2, right? 8 and 6, 6 and 4, 5 and 3, 4 and 2. And then whatever number I got, I just multiplied that by 180, and that gave me the total number of degrees. And that is actually the internal angle of a polygon theorem. It says for any polygon, like let's say I'm trying to find the total degrees of a dodecagon, then I know that a dodecagon has 12 sides, I would subtract 2, and I would multiply it by 180. Okay, so 10 times 180 is 1800. So if I measure all the inside angles of a dodecagon and add them up, I would get 1,800 degrees. Right? And that is what these theorems are saying. The sum of the interior angle measures of a convex polygon with n sides is n minus 2 times 180. All right? Then the exterior angle theorem is a little easier because it always is the same. no matter what kind of polygon it is, as long as it's convex, um, no matter how many sides it has, no matter what the shape is, as long as it's convex, it always has an x. If you add up all the external angles, I always get 360. Okay? So if I want to find the sum of the interior angles of a decagon, a decagon has 10 sides, so I plug it into my formula. The number of sides minus 2 times 180, and I get 8 times 180, which is, let's see, 8 plus 6, 1440. If I want to find the interior angles of a 15-gon, I would do 15 minus 2 times 180. So that's 13 times 180, which is 20, oops, that didn't work, 2340. Okay? Okay, and what would the measure of each angle of a regular hexagon be? Well, if I have a hexagon and it's regular, which means all the angles are equal, I could figure out how much the total is by doing 6 minus 2 times 180. 4 times 180 is 720. And since it's regular, I know that each angle is equal. So I would just have to split that 6 ways, and that would be 120. So each angle would be 120 degrees. To figure out this, I would add up all the sides. So 4y plus 4y plus 4y minus 9 plus 3y plus 11 plus 103. And I know that all together that should equal, well, there are 1, 2, 3, 4, 5 sides, so 5 minus 2 times 180. 3 times 180 is 540. So I know that all of this added together is 540. And then I'd combine like terms and I'd solve. Right? We're getting out of time here, so I'm going to go quick. Now, again, it's kind of easier for external angles. Here's my 4 external angles. Remember, you get external angles by extending the sides of the shape. And I know that no matter how many sides it has, the angle is always equal 360. So the more sides the shape has, you can assume the exterior angles are going to be smaller. But anyway, to solve this, I would just add up all my angles and set it equal to 360 and solve. Okay? So why don't you take a minute and see if you can figure out what x is here.